Hi everyone, I'm really glad to welcome everyone to this wonderful event and to share something new and exciting with you. In my talks, I usually focus on two things, either new, lesser known technologies or old but overlooked ideas that I believe deserves more attention. And this topic is no exception. I'm going to talk about something experimental but with a lot of potential. It is a Scheduler.yield. Right now this feature is still in early stages and not all browsers support it yet, but there's already polyfill available, and during the talk I'll also show some alternative ways to achieve similar behavior. These aren't perfect replacements, but they can still be useful in the meantime. And before we dive into the topic, just a few words about myself and why it might be worth listening to what I have to say. I'm a front-end engineer with over 6 years of experience, author of technical and scientific publications, and speaker at global tech conferences. I'm a mentor and judge at international hackathons and innovation award programs, and I'm also involved in the open source community program contribution, including creating my own open source CSS library Skeleton Mammoth. I am also a member of several professional associations. Now that you know a little bit about me, let's get to the point. So, what is a Scheduler.yield? It is a method of the scheduler interface from the new prioritized task scheduling API. This method allows you as a developer to pause your JavaScript execution and explicitly yield control back to the main thread, so it can handle other pending important tasks like user interactions, clicks, typings, etc. In simple terms, when you call Scheduler.yield, you are telling the browser, wait, take a breath, let's pause the current task and focus on other no less or more important tasks. Once you have done, come back and continue execution from where we left off. This makes your page more responsive, especially when running long or heavy JavaScript tasks. It can also help improve metrics like interaction to next pane called INP, which is all about how quickly the browser responds to the user input. Before we dive deeper, let's quickly go over a few basic terms that I'll be using throughout the talk. I'm sure many of you already know them, but a quick refresh never hurts. Main thread. This is a central place where the browser does most of its work. It handles rendering, layout, and runs most of your JavaScript code. A long task. This is any JavaScript task that keeps the main thread busy for too long, usually more than 50 milliseconds. When that happens, the page can freeze or feel unresponsive. And the blocking task is a synchronous separation of the main thread that prevents the browser from processing other important things, like responding to clicks or updating the UI. Usually long tasks are blocking tasks. The problem. To understand the beauty of Scheduler.yield, we first need to understand what problem it's trying to solve. And for that, let's quickly refresh how JavaScript processes tasks. In other words, how the task processing in the browser works. I'm sure many of you have seen diagrams like this before, the task queue, the event loop, the call stack. This one isn't perfect, but it gives us the big picture. Let's walk through the main ideas step by step. So, all synchronous code goes straight to the call stack and runs line by line, function by function. It follows the LIFO principle, last in, first out. JavaScript runs in a single thread, which means it can do only one thing at a time. Asynchronous operations, set, timeout, fetch, are handled outside the main thread by the web APIs, provided by the browser or environment. Once they're done, they don't go back directly into the call stack. Instead, their callbacks are queued either in the microtasks queue, you can see it here, like promise then, queue microtasks, or tasks queue, set timeout or set interval. When the call stack is empty, the event loop checks the microtasks queue and runs all microtasks one by one in order. Only after that, it takes one runnable task from the chosen task queue. Importantly, the task queue are sets, not strict FIFO queues. The event loop picks the first task that is ready to run, not necessarily that one that was added first. If, during the process, new microtasks are added, they are run before the next task from the task queue, so microtasks always get priority. This loop keeps going, all microtasks, one task from task queue, repeat. New synchronous code gets into the call stack when new tasks arrive, like a user clicking a button, a new script being run, or when a microtask or task from task queue runs its callback. This is a very brief and superficial explanation just to remind you how it works, since it will further closely intersect with the topic. Please note, the event loop itself is not part of the JavaScript ECMAScript specification. If you look into the ECMAScript specification, you won't find it there at all. The event loop is defined in the HTML standard. The problem description. Now that we have refreshed our understanding of how JavaScript executes tasks, let's take a closer look at the real problem that comes with this model. The issue is simple. When a task takes too long on the main thread, it blocks everything else. User interactions, rendering updates, and animation. This leads to UI freezes and pure responsiveness. The obvious first thought might be, just don't write long or heavy functions and that's it, the problem is solved. And yes, that's true. In an ideal world, we would always split heavy code into smaller parts, optimize everything, and avoid blocking the main thread. But let's be honest, many of us have run into these issues even if we weren't the ones who originally caused them. Even if you were not the culprit of this behavior, you have to work with it. And to make this more concrete, let's simulate a simple but realistic case. Imagine we had to process a large array and each element requires some non-trivial computation, something that takes time and uses CPU, which in turn blocks the main thread. For this, we will create a function called blocking task that acts as a blocking task for the main thread for the specified period of time. The function simulates this kind of heavy computation on each element of the array. There's nothing fancy about the function, here's all it does. So it accepts an argument, the number of milliseconds. This is the minimum time the function will run, thus occupying the main thread. Then it creates an empty array, then it creates a start time as a current time, and then runs a while loop until the specified time has passed. Inside the loop, it just does random, meaningless calculation to simulate load. Finally, it returns the result of the calculation. The function doesn't do anything useful, but it does simulate a real-world scenario of heavy load. This function will be used inside another simple function. Imagine a common situation where we need to loop through an array of data and apply that heavy work to each item of the array. To do this, we will create a heavy work function in which the following happens. On line 2, it creates an array of 200 items, just numbers from 0 to 199. I want to know that 200 items are not that many, but it will be enough to see the essence of the problem. Then a new empty result array is created to store the processed values. Then on line 5 declares a loop that goes through the entire length of the data array. Inside the loop, we run the blocking task function, simulating only 10 milliseconds of work for each element, and the result is added to the result array. Once again, I want to remind you that for the demo, the blocking task function does not carry any semantic load. It simply performs some imaginary resource-intensive work. In the real world, it could be some labor-intensive processing of an array element. Finally, it returns the resulting array. And that's where the amazing part comes in. Just 10 milliseconds per element and only 200 elements, but together they block the main thread for 2 full seconds. That's enough to cause a noticeable freeze in the UI. No clicks, no typing, just a frozen page. The problem demonstration. Now it's time to look at the problem not just in theory but in action. This is not full-fledged demo just yet. Think of it as a simplified visual to help you clearly see the issue. Here's what you see here. The left window titled configuration lets you turn on the main thread blocking on and off, meaning whether the blocking task function is actually running. You can also toggle Scheduler.yield functionality, we will get to that part later. The window titled heavy task here on the right runs the heavy work function. This is one that processes an array using blocking task on each element if the main thread blocking is enabled. And the window titled logger here just logs the current time to the console, including milliseconds. Let's see what happens when the main thread blocking is turned off. So the tasks are very light, it just took over an array of 200 elements without any complex calculation. What we observe here. The user clicks the OK button, the heavy work function runs and instantly returns. This is indicated by the message heavy task done in the console, followed by the result of an array of numbers here. Then the user clicks the log button 3 times. They log the time to the console. Timestamps appear immediately with a slight difference in time. They run the heavy work function again and again instant response. Finally, the user closes 2 windows, which actually just remove those elements from the DOM. No delays, no hiccups. In this case, everything feels fast and responsive. The browser has no trouble handling the interactions because the main thread stays free. Tasks are performed almost instantly and consistently. Now, let's enable the main thread blocking so that for each element of the array, the blocking task function will be called with a delay of only 10 milliseconds. And now you can observe that user interaction with UI elements has become less smooth, UI freezes have appeared. Let's break it down to what is happening here and what we can observe from it. The user presses OK button, thereby launching the heavy work function. And the first lag that occurs is that the OK button visually stays pressed. Why? Because the browser cannot repent while heavy work is still blocking the main thread. And it is important to understand that we are talking not only about the current task, but about the call stack as a whole. During this time, the user clicks the logs button 4 times, nothing happens. The clicks are registered and their handlers added to the queue, but the browsers can't react. Only after heavy work finishes do we see the console output. First the heavy work result, then the 4 time steps, all printed in a batch, and only after that the OK button changed its state and became impressed. Next, the user clicks OK button again. Same behavior, stack button, then while the heavy work task is running, he tries to close the window by clicking the X icon 3 times. Again, no visual response, only when the task ends do we see the window disappear. And finally, one more attempt to run heavy work and close the last window, same freeze. So, you see the pressed button, you see nothing happens here, you see the pressed button again, nothing happens, it's laggy, it's freezed. What does this show? This simple demo shows how long tasks block the browser's ability to respond to user interactions. Even though each blocking call takes just 10 milliseconds, chaining 200 of them together results in a 2-second freeze. The user can't interact with the buttons, the interface doesn't repaint. Events get queued up but not processed until the call stack is clear. This is not just a performance issue, it's a user experience problem, and that's exactly the kind of issue we want to solve, ideally without having to manually split our logic into dozens of callbacks. The problem solution. Now that we understand the problem, let's talk about the possible solutions. Of course, the best strategy is to avoid long tasks in the first place by keeping code efficient and breaking things up early. But, as we have seen, stuff happens. Whether it's legacy code, unavoidable computation, or just not enough time to optimize, sometimes we have to deal with it. Over the years, before the prioritized task scheduling API appeared, various workarounds and tricks have been come up with to improve the responsiveness. But the core idea behind all of them and behind Scheduler.yield as well is pretty simple. Break a task into smaller pieces, chunks, and once in a while pause to let the browser catch its breath. In other words, we give the main thread a chance to run more urgent tasks like user interactions or rendering updates, and then we come back to finish our own work. Here's what the concept of heavy work function looks like in the pseudocode. What's happening here? First, you run a chunk of your task. Then, you pause allowing the browser to handle other high priority tasks like UI updates. Pause the current task and pass control to the main thread to handle other high priority tasks. And then continue execution the function from where it left off. Old problem-solving approaches. Before Scheduler.yield came along, the most common trick for dealing with the long blocking task was to use setTimeout. By calling it with a 0 delay, you add its callback task to the end of the task queue, allowing other tasks to run first. In other words, you tell the browser, run this bit of code later, after you have handled everything else. That's how we can give the main thread a short breather between chunks of heavy work. Here's what the updated heavy work function might look like using this approach. Let's break it down what's going on here. On line 3, a promise is created and its executor runs immediately, scheduling a set timeout with a 0 delay. The timeout callback which resolves the promise is added to the end of the task queue. Because of a wait, the rest of the async function is paused. Technically, this continuation is added to the microtask queue, waiting for the promise to resolve. The JavaScript engine checks the call stack. Once it's empty, the event loop kicks in. First, it looks at the microtask queue, but since the promise isn't resolved, there is nothing to run. The event loop picks the task from the queue. In our example, it is setTimeout callback. Runs it, and this resolves the promise. Now that the promise is resolved, the microtask containing the continuation of the async function is run. In simple terms, line 3 gives the browser a chance to catch its breath before heavy work begins. Therefore, by calling this method before doing any heavy work gives the browser a moment to re-render UI updates, such as unfreezing a clicked button. On line 9, we calculate how often we want to yield to the main thread. Roughly every 25% of the work. This number can vary depending on how heavy the task is. On lines 13 through 15, inside the loop, if the condition for yielding interval is met, execution is transferred to the main thread. That is, the setTimeout technique is repeated, allowing the browser to process user interaction or redraw the interface. Essentially, this approach works. It's relatively simple and does improve responsiveness. But there's a trade-offs. One big issue that is setTimeout isn't built for precise scheduling. It puts tasks at the end of the task queue, and anything already in that queue can delay your continuation. For example, let's say some other part of the page uses set interval to run task regularly. Now your own task, the next chunk of heavy work function, might get delayed by one or more of these interval callbacks. The browser just runs whatever is next in line, and you don't control the order. So, while set timeout lets you yield, you don't know exactly when you will get control back. There are other ways to approach this situation. It could be the request animation frame function, which lets you schedule work right before the next repaint, often used in conjunction with the set timeout and has similar drawbacks. Or request idle callback that runs your code during a browser idle time. It's not quite an alternative, but good for background, a less important work that helps the main thread to be free for more critical tasks. In general, we could discuss other strategies for solving and preventing such problems. However, to stay on topic, let's move on and see what Scheduler.yield brings to the table. So, Scheduler.yield, it is a modern way to pause execution and yield control to the main thread, which allows the browser to perform any pending high priority work and then continue execution from where it left off. What actually happens under the hood? When the await Scheduler.yield expression is reached, the execution of the current function in which it was called is suspended, and yields control to the main thread, thereby breaking up or pausing the current task. The continuation of the function, that is the execution of the remaining part of it from where it left off, is a separate, newly scheduled microtask in the event loop. The beauty of Scheduler.yield is that the continuation after Scheduler.yield remains at the front of the queue and is scheduled to run before any other non-essential tasks that have been queued. The key difference from the set timeout approach is that with set timeout, these continuations typically run after any new tasks that have already been queued, potentially causing long delays between yielding to the main thread and their completion. The following diagram illustrates how three approaches compare in practice. Let's look at them. In the first example, without yielding to the main thread, at the first the long task 1 runs uninterrupted, blocking the main thread and UI accordingly. Then a user event is processed, a button click triggered during the execution of task 1, and finally task 2 is executed. Set timeout callback scheduled earlier during the execution of the long task. In the second example, using set timeout as a yielding to the main thread, the execution queue is different. At first, the long task 1 runs. Then, when the yield to the main thread happens, task 1 pauses to let the browser breathe and the button click is processed. But after the button click is processed, the set timeout callback will be executed first, which could have been scheduled in advance or during the execution of task 1. And finally, only after that, the continuation of task 1 will be executed. And in the last example, using Scheduler.yield technology, after the long task 1 has been paused and the user click event has been processed, then the continuation of the task 1 is prioritized and runs before any queued set timeout tasks. In summary, Scheduler.yield is a more intelligent and predictable way to give the main thread breathing room. It avoids the risk of your code being pushed far too back in the queue and helps maintain performance and responsiveness, especially in complex applications. Priorities. So, what causes such a difference in behavior? It's all about priorities. As developers, we don't usually think about the order of execution of tasks in the event loop in terms of priorities. More precisely, we have a good understanding of what microtasks and task queue are and the order in which they run, but if you look deeper, you will notice that there are also implicit priorities at play. For example, a button click handle fired by user action will typically execute before a set timeout callback, even though both are tasks from the task queue. As mentioned earlier, Scheduler.yield is a part of the prioritized task scheduling API, an extensive and future-rich interface that deserves its own separate full-fledged discussion is clearly beyond the scope of this talk. Nevertheless, it's important to mention one of its key features, the introduction of a clear task priority model. Prioritized task scheduling API simply make these priorities explicit, making it easier to determine which task will run first and enables adjusting priorities to change the order of the execution, if needed. Here's a quick look at the main priority levels it defines. First, it's user blocking, the highest priority tasks that directly affect user interaction, such as handling clicks, taps, and critical UI operations. Then, user visible, tasks that affect UI visibility or content but are not critical for immediate input. And the third, background, tasks that are non-urgent and can be safely postponed without affecting the current user experience and are not visible to the user. By default, Scheduler.yield has a user-visible priority. Also, Prioritize Task Scheduling API exposes the post-task method, designated to schedule tasks with a specified priority from the above. While it won't go into details about this method here, it is worth mentioning that if Scheduler.yield was scheduling from within a post task, it inherits its priority. So how to use Scheduler.yield? And once you understand how it all works, the types of tasks, the problem caused by long blocking operations, and the priorities, the use of Scheduler.yield becomes straightforward, but it should be used wisely and with due caution. Here is an updated version of the heavy work function using Scheduler.yield. Now, instead of set timeout, you just need to call await Scheduler.yield, and the rest part remains unchanged. Here and here, instead of set timeout, we're just calling await Scheduler.yield. Now, when a user starts a heavy work function using Scheduler.yield, the difference is immediately noticeable. Firstly, the OK button does not stick, and secondly, user click events on the log button are successfully processed, which does not block the user interaction with the page. That is, at first, the heavy work function was launched and the button was re-rendered without sticking. While the heavy task was being executed, the user pressed the log button. The event was processed successfully and the data was printed to the console. Then the heavy work function continued and its final result was printed to the console. After the completion, the user pressed the log button again. In short, you can give your browser a break with just one line. So you can see that there are no UI freezes. We can see the log almost immediately. Now that we have explored the theory, let's move on to the practice and look at a real working demo. This is a simulated banking application. Of course, it's fictional and simplified, but it captures just enough of the real-world complexity to help us understand how blocking the main thread affects interactivity and how Scheduler.yield can help. Here's what the user sees in the interface. Balance section. By default, the account balance is hidden behind a placeholder of asterisk. This is a familiar pattern in the real banking apps, where sensitive information is hidden unless explicitly revealed by the user. A button labeled Show Balance toggle visibility. Next, a bank card, a visual representation of a bank card shown front side by default, where some details are displayed: card type in the top left corner, last 4 digits of the cardholder's name, and the payment system at the bottom right of the card. There are 2 buttons to the right of the card. Show card details, which flip the card when clicked. The back side of the card reveals sensitive card data like its full number, expiration date, and CVV code. Although the card number is generally not considered private information, some applications still prefer not to show the full number by default, but only if the user initiates it. However, I know and even use the banks that generally do not allow you to see the bank card number even in the application. And generate report. By clicking this button, the feature supposedly generates a list of transactions on the card and displays them in the table below. This imitates the real functionality where a user can generate reports on the bank card transactions. In reality, these reports can be complex tables with many customizable filters and the ability to download the reports as a file. Such operations might involve heavy computations, process a huge amount of data, making them resource-intensive and time-consuming. For the sake of the demo, it's simplified. Under the hood, the Generate Report button triggers the previously discussed heavy work function, which simply blocks the main thread using the blocking task function, which was also discussed above. After that, static mock transaction data is simply rendered into the table. The behavior of the application can be customized using the various settings of the configuration panel on the left side. You may have noticed its simplified version in earlier screenshots. Now it's time to explain what it does. Main thread blocking determines whether the main thread will be blocked. In fact, when this option is enabled, the blocking task function is executed. Scheduler.yield toggles whether Scheduler.yield is used. Data array length controls how many elements are iterated by the heavy work function. The more elements, the longer it takes. Blocking time durations specifies how many milliseconds each element of the array takes to process. And the yield interval defines how often Scheduler.yield is called as a percentage of progress through the array. That is, the lower this number, the more often it will be called. In earlier example, we used a 200 element array with a 10 milliseconds delay and a 25% interval, a good balance for visible impact without excessive delay. With larger datasets, a smaller interval is often better, but as always it depends. Having sorted out all the functionality and configuration, let's walk through the real user scenario and see how blocking the main thread affects the user experience. To start, we enable main thread blocking and disable Scheduler.yield. We also increase the array length a bit so the heavy operations take longer given as the time observes the effects. So the user clicks the generate report button behind the scenes. This triggers the heavy work function, which processes 1000 elements where each element takes 10 milliseconds. Watch what happens. The generate report button stays stuck, it doesn't unpress and the UI doesn't re-render. While the report is being generated, the user tries to click the show card details, then the show balance buttons, but nothing responds. The interface is completely frozen. There is no animation, no feedback, no sense of progress. This is a classic example of a bad user experience. The app appears frozen, even though it's technically still working. The user doesn't know whether to wait or load the page. And let's address these shortcomings using Scheduler.yield by adjusting some configuration. Here's how the configuration now looks. The main thread is still blocked. This time the option to use Scheduler.yield is enabled. The array length is slightly increased. Just for clarity, the blocking time remained the same 10 milliseconds. The Scheduler.yield response interval is reduced to 5% for smoother responsiveness and the array length has been increased. And now with the updated configuration, the same user flow looks completely different. The first thing that catches the eye is that after the generate report button has been clicked, it re-renders correctly and the loading animation appears. While the report is being generated, the user successfully interacts with the UI. They can flip the card and toggle the balance. The application remains responsive even if the animation are slightly less smooth. It's a huge step forward compared to the previous freeze. This is a much better experience. The user is informed, in control and not left guessing whether the app is working. And all it was one method called just Scheduler.yield. Of course, the actual implementation can be further optimized, but even this simple form, the difference is striking. And as a conclusion, I want to say that today you learned about giving your browser a break, the importance of yielding to the main thread that perform higher priority tasks, and the advantages and the disadvantages of these techniques. There are certainly more nuances to cover, and the prioritized task scheduling API has other capabilities that were not covered in this talk. But my goal was to give you a solid foundation enough to start experimenting and enough to start thinking differently about how your code plays with the browser. Thanks for your attention and give your browser a break once in a while.